Imagine holding two objects in your hands. One is the hardest natural substance known on Earth, capable of cutting steel and lasting billions of years. The other is soft, dark, and fragile, leaving marks on paper with the slightest pressure. At first glance, these two materials seem to have nothing in common. Yet, at the most fundamental level, they are made of exactly the same element. That element is carbon. This is the story of diamond and graphite, two minerals that prove how powerful atomic structure can be, and how a single element can create completely different worlds. To understand diamond and graphite, we first need to understand what a mineral is. A mineral is a naturally occurring, solid, inorganic substance with a definite chemical composition and an ordered internal atomic structure. This definition is strict, and many substances do not qualify. Diamond and graphite, however, meet every requirement. They form naturally within the Earth, they are solid under normal conditions, they are inorganic, they have a definite chemical composition, and their atoms are arranged in highly ordered structures. Because they are made of only one element, they are also classified as native element minerals. The element that connects diamond and graphite is carbon. Carbon is element number 6 on the periodic table and is one of the most important elements on Earth. It forms the foundation of all known life, plays a key role in Earth's atmosphere, and is a major component of rocks, fuels, and organic materials. What makes carbon especially unique is its ability to bond strongly with other atoms, including other carbon atoms. This bonding flexibility allows carbon to form different structural arrangements known as allotropes. An allotrope is a different physical form of the same element caused by a different arrangement of atoms. The chemical composition does not change, only the structure does. Diamond and graphite are two of the most well-known allotropes of carbon. Although both consist entirely of carbon atoms, their internal structures are completely different, and this difference is responsible for their contrasting properties. In diamond, each carbon atom is bonded to 4 other carbon atoms. These bonds form a 3-dimensional tetrahedral structure, creating an extremely rigid and stable lattice. Every atom is tightly locked into place, and there are no weak points within the structure. When force is applied to a diamond, it is distributed evenly throughout the entire crystal. This atomic arrangement explains why diamond is so incredibly strong. As a result of this structure, diamond has remarkable physical properties. It is the hardest naturally occurring mineral, ranking a perfect 10 on the Mohs hardness scale. Diamond can scratch nearly every other material found in nature, and it can only be scratched by another diamond. This hardness is not just a surface property, it is a direct result of the strong covalent bonds holding the carbon atoms together in all directions. Diamond is also typically transparent. Light passes through its tightly bonded lattice and bends strongly within the crystal. This bending of light produces brilliance and dispersion, which is why diamonds sparkle when they are cut and polished. In addition, diamond does not conduct electricity because all of its electrons are tightly held in covalent bonds, leaving no free electrons to carry an electric charge. However, diamond is an excellent conductor of heat, even better than many metals, which makes it useful in advanced electronic applications. Because of these properties, diamond has many uses beyond jewelry. Industrial diamonds are widely used in cutting tools, drill bits, grinding wheels, and polishing equipment. They are essential in construction, manufacturing, and medical technology. While gem-quality diamonds are prized for their beauty and rarity, industrial diamonds are valued for their strength and durability. Graphite, on the other hand, tells a very different story. Although it is made of the same carbon atoms, its atomic structure is arranged in a completely different way. In graphite, each carbon atom is bonded to only 3 other carbon atoms. These bonds form flat, hexagonal sheets that extend in 2 dimensions. Within each sheet, the bonds are strong and stable. However, the bonds between the sheets are very weak. This layered structure is the key to graphite's properties. The sheets are held together by weak forces that allow them to slide easily over one another. Because of this, graphite is very soft and easily breaks apart along these layers. It ranks only about 1 to 2 on the Mohs hardness scale and can be scratched with a fingernail. Graphite is typically black or dark gray and completely opaque, meaning it does not allow light to pass through. It often has a dull or slightly metallic appearance. The layered structure also gives graphite a slippery feel, which is why it is used as a lubricant in many industrial applications. One of the most important differences between graphite and diamond is electrical conductivity. Unlike diamond, graphite conducts electricity. This happens because some electrons in graphite are not tightly bound to individual atoms and are free to move between the layers. These free electrons allow electrical current to flow, making graphite useful in batteries, electrodes, and electrical devices. Graphite is perhaps most familiar as the material used in pencils. Despite the common term pencil lead, pencils do not contain lead at all. They contain graphite mixed with clay. When you write, thin layers of graphite slide off onto the paper, leaving behind visible marks. This simple action is a direct result of graphite's layered atomic structure. In addition to pencils, graphite is used in many important applications. It is found in batteries, electric motors, brake linings, lubricants, and even nuclear reactors, where it is used as a moderator to slow down neutrons. Though it may seem ordinary, graphite plays a crucial role in modern technology. When diamond and graphite are compared side by side, their differences are striking. Diamond is hard, transparent, electrically insulating, and extremely durable. Graphite is soft, black, electrically conductive, and easily broken apart. Yet both are made entirely of carbon. The only difference is how the atoms are arranged. The way these minerals form in nature further highlights their differences. Diamonds form deep within the Earth's mantle, more than 150 kilometers below the surface. They require extremely high pressures and temperatures to form. Under these conditions, carbon atoms are forced into the dense, three-dimensional structure of diamond. Diamonds are brought closer to the surface by powerful volcanic eruptions, carried upward in rocks called kimberlite. Graphite forms under much lower pressures and temperatures. It commonly develops during metamorphism, when existing rocks are altered by heat and pressure, or it crystallizes from magma. Because these conditions are more common than those required for diamond formation, graphite is far more abundant on Earth. The relationship between diamond and graphite demonstrates one of the most important principles in science. Structure determines properties. Chemical composition alone does not define how a material behaves. Instead, it is the arrangement of atoms that controls hardness, strength, conductivity, appearance, and usefulness. This principle extends far beyond geology. In chemistry, biology, and material science, small changes in structure can lead to dramatic changes in behavior. Scientists use this knowledge to design new materials, such as synthetic diamonds, graphene, and carbon nanotubes. Each of these materials is made of carbon, yet each has unique properties due to differences in atomic arrangement. Nature discovered this principle long before humans did. Diamond and graphite are natural examples of how powerful atomic structure can be. They show us that even the simplest elements can produce extraordinary diversity. The next time you see a diamond sparkling under bright lights or write a simple note with a pencil, remember what lies beneath the surface. Both objects are made of carbon, both are minerals. Both form naturally within the Earth, yet their atomic structures place them in completely different worlds. Diamond and graphite remind us that in science, the smallest details matter the most. A tiny change in how atoms are connected can transform softness into hardness, darkness into brilliance, and simplicity into strength. Same element, different structure. Completely different reality. As we come to the end of this journey, one idea stands above everything else. Diamond and graphite remind us that what something is made of is not always as important as how it is made. Both minerals are formed from the same element carbon, yet their atomic structures place them at opposite ends of the physical world. One becomes the hardest natural substance on Earth, while the other becomes soft enough to write with. This contrast is more than just an interesting fact. It is a powerful lesson in science. It shows us that tiny changes at the atomic level can create enormous differences in strength, appearance, and usefulness. From the brilliance of diamonds to the simplicity of graphite, nature demonstrates that structure controls behavior. So the next time you see a diamond sparkle or pick up a pencil to write, remember the story hidden inside. Two materials, one element, and a single difference in atomic arrangement, proving that even the smallest building Blocks of matter can shape entirely different worlds.